Now let us consider what happens for bound states. So for bound states, if I have a bound state, phi n of x of energy En, let's see what the fact that the parity and Hamiltonian operators commute, what that tells us about this type of a state. So we're back to now quite general conclusions that in fact would work for any symmetry operator. Well, I can, because these operators commute, I can write this down as P acting on H acting on phi n of x has to be exactly the same thing as H acting on P acting on phi of x, phi n of x. And the reason that I can say this is the symmetry. This comes directly from the symmetry of the Hamiltonian. Now, to make progress on this, I want you to notice that if phi n is truly a bound state of energy En, then I know that this Hamiltonian applied to it gives me nothing other than that energy times my state phi n back again. So, and then of course the parity operator is a linear operator, so I can pull out the energy En. So this gives me then the next statement that I can make, which is that En multiplying p hat applied to phi n of x is in fact the Hamiltonian applied to the parity operator applied then again to phi n of x. So what allowed me to make this next statement was the fact that phi n is a bound state. Now, as you'll notice, the conclusions here come pretty quickly without a tremendous amount of algebra. This is a very general set of results. If you look at this equation, right, E times this gives me my Hamiltonian times this. So I immediately now know I can say that p hat times phi n of x, right, is also a bound state. And that comes just from our quantum purity test. Because applying the Hamiltonian to this thing, whatever it is, gave me back the energy En times times that function. It's a bound state of energy, and it has that particular energy value E sub n. But if that's true, then I know something very interesting, because I know that these bound states are non-degenerate. So any bound state, in particular the bound state P phi n of x, must equal, in fact, just some arbitrary normalization constant, right, times then the bound state, because there's only one of them. And the name for that bound state of energy En is phi n. So this statement comes about actually from the non-degeneracy of the states, of bound states, specifically in D equals 1 dimension. While we're at it, I should point out that this conclusion here had nothing to do with the fact I was in one dimension. This actually applies generally. So in general, what we learn is that if I have a pure state of energy, a pure bound state, I apply any symmetry operator to it that the Hamiltonian respects, it will generate for me automatically another state of the same energy. If there's only one state, if it's a non-degenerate state, I get this nice relation, and I can conclude something very quickly from this. If, on the other hand, it's not a degenerate system, things get very interesting. They then begin to relate to a more complex mathematical theory known as complex representations of groups. We're not going to get into that in detail here because even the one-dimensional case for us is going to be quite interesting. So if we continue focusing on the one-dimensional case, I know this is a bound state of energy En, so it must just be a normalization times my one existing bound state. But if I look at this relation, this is just the quantum purity test for the parity operator. So that gives me the reason for this is quantum purity of quantum purity test for the parity operator. So therefore, we can conclude that phi n of x is a pure parity state. And that's very exciting because this is a pure parity state, right? That means immediately it is either an even function or odd. And so we're led inexorably to this conclusion simply from the fact of this commutation relation. So we've proved it then. If we have a symmetric potential, H will commute with the parity operator, and therefore any solution, any bound state solution, is going to be an even or odd function. So that completes our proof of this major claim, which corresponds to the observations that we had made for the finite square well. So that, again, deserves a happy professor symbol. We've completed the proof we had set out to prove.